Hi, this is Miss Dahlberg. Welcome to AP Chemistry. Today we're talking about Thermodynamics 3, and today we're going to be talking about something called entropy, which we know as delta S, and we're also going to talk about free energy, which we know as delta G. And so let's get started. So if we're talking about whether or not things happen, we're going to talk about something called thermodynamically favored. And we're going to talk about a few different processes, like water evaporates at room temperature. If you have iron and there's oxygen and water in the environment, it will rust. You do not have to do anything for those things to happen. If you put table salt, sodium chloride, in water, it will dissolve. You do not have to stir it. If you stir it, it might happen faster, but it does it without any help. And if you have a reaction that happens without any extra help, it's called a thermodynamically favored process. Another word for that sometimes used is a spontaneous process. So there are certain things that are not thermodynamically favored. It won't happen without extra help. Like, for example, water, if you have it at 75 degrees Celsius, it will not boil. The only way to make water boil at 75 degrees Celsius is to change the pressure. If you change the pressure, you can make water boil, but that's the only way you can do it. Water will not freeze at 15 degrees Celsius. Iron ore or rust will not react with carbon to form metallic iron. The only way to make that happen is a process called smelting, where you have this reaction occurring at tremendous temperatures. And so these are all non-spontaneous processes or non-thermodynamically favored. So if you have something that is thermodynamically favored in one direction, the reverse reaction is never thermodynamically favored. And so the opposite is always the inverse of that. So if you have, we talked about exothermic reaction. So when we talk about delta H, if you have an exothermic reaction or you have delta H is negative, they are often, most of the time, thermodynamically favored. That tends to be a process that's thermodynamically favored. Why? Because the bonds of the product have less energy. There's less energy in the bonds, and so that's a lower potential energy state. And so nature tends to favor those. But sometimes you can have an endothermic reaction where delta H is positive. Sometimes those are thermodynamically favored, so you can't look at delta H to determine that. For example, water. Water in the liquid form going to the gaseous form, you have to add energy in for that to evaporate. And so that's an endothermic process. This happens on its own without us doing anything. And so that's a thermodynamically favored process. And so you can't look at just delta H. We also need to look at something called entropy. Now, entropy is the disorder of a system. And if you have more disorder, that tends to be thermodynamically favored. And a positive value for delta S means you have more disorder. And so if you have more disorder in the products, this is a bigger positive number than in the reactants, then you have a change in entropy that's bigger, or a bigger positive number, so you have more disorder. So let's look at a few things. So if you look at that, examples of this, entropy has to do with the disorder. If you look at your house never just gets clean. It always somehow over time becomes dirty. Things become more disordered in your house. If you start making a stir fry, you can never get those ingredients back to the order that they were before, all the bell peppers together, all the onions together, without doing a lot of work. And so all of these things represent increases in entropy, and they tend to happen whether we want it to, in the case of your room, or not getting dirty or not. And so if we look at the laws of thermodynamics, the first law of thermodynamics is one you've known for a long time. It says the energy contained within the universe is constant, and that is the law of conservation of energy. Now, the second law of thermodynamics says that the entropy or disorder of the universe is constantly increasing, meaning our universe is constantly getting more disordered. And we know that because of this, our universe is expanding. Now, if we look at delta S for the following processes, for melting, going from a solid to a liquid, or vaporization, going from a liquid to a gas. Those are increases in disorder if you think about those. The particles are more arranged for a solid, and now they're sliding about each other for a liquid, so there's more disorder. There's more arrangements of those particles. For vaporization, for a liquid, you have the particles that are freely flowing, but if you think about from a liquid, they're all kind of in these like random little arrangements. There's a lot more arrangements for those, but if you look at a gas, they are moving everywhere, and there's more arrangements for a gas, and so there's more potential for disorder for a gas. In fact, this is an increase in disorder, a positive delta S. This is a much bigger increase in disorder, or a bigger positive number for delta S. And so another thing where you have a positive delta S, if you have products in the same phase as the reactants, but you have more moles, it says particles, but we can think about this. You have more moles of products than in the reactants. That's an increase in disorder. Most of the time, not all the time, but most of the time, when you take something and dissolve it, if you take a compound and dissolve it in a solution like water, it's more disordered. There are a handful of times where there's an exception to that, but most of the time, there's more disorder. If you add heat, you make the particles move faster, and so there's more disorder. And anytime you increase the volume of a gas, you increase the amount of space, and you increase the amount of arrangements or the places the gas can be, and so that is also more disorder. And so anytime you have a situation like this, you have a solid go into a liquid, this is, especially when you look at the picture, easy to see that it's less disordered. I mean, less organized, so it's more disordered. So you're going to have a more positive delta S. So here, look at this. We have a liquid that's kind of disordered, but this is a huge amount of disorder compared to the previous situation. And so that's a really, really high. There's a huge change in the value for the entropy there. Okay. So let's look at this reaction here. And so if we look at this, this is nitroglycerin, and we look here, we have 4 moles of a liquid, and when this reacts, we go from 4 moles of a liquid, not to just to gas, but we go to 29 moles of a gas. And so that is a tremendous increase in disorder. And so this is a really good example. If it just went to 4 moles of a liquid to 29 moles of a liquid, that would be an increase of disorder, a very positive delta S. But since it's a gas, it's this tremendous increase. And in fact, you might be a little bit familiar with it. This reaction has an interesting history. If you look up, you can read lots of stories about disasters where they use this compound which is kind of like an oil, to lubricate wagon wheels, which caused an explosion. Sometimes warehouses or boats with this stuff would just randomly explode. And if you look at this, this reaction can, in like a millisecond, cause an increase, depending on the amount, of like 270,000 atmospheres of pressure in an instant, in 1 times 10 to the minus 6 of a second, which is a tremendous amount of pressure in a small amount of time. Well, one of those warehouse explosions killed a brother of a guy named Alfred Noble. And Alfred Noble, his family had warehouses of this stuff. And so he came up with a way to take this nitroglycerin and kind of stabilize it. And so he took the remains of these microscopic sea creatures, called this stuff called kilsagar. And what he did was, it's kind of like a paste. He made a paste out of it and encapsulated the nitroglycerin in a paste and made it a little bit safer. And then he made a little fuse out of gunpowder, and we know that as dynamite. Well, the nitroglycerin had a lot of uses, but once it was stabilized, the dynamite wasn't just used for example, in mining applications. Then it started being used for war applications. Well, just like there's a lot of fake news on the internet now, there was a newspaper article published with his obituary, and kind of like today, he wasn't actually dead. So imagine if you get to see your own obituary and you are known as the agent of death. Well, Alfred Noble didn't like that, and so he went about to change his legacy, and he actually invented something you might have heard of called the Nobel Prize. And so now he's famous for starting the Nobel Prize, which awards a large cash and prestige award onto the recipients in several categories. And so I thought that was an interesting little side article here. And so let's continue. Here is an example of an ionic compound. If you have an ionic compound, you have a crystal lattice structure. It's extremely ordered, very, very ordered. When you put it in like a solution of water, and all of these ordered little ions break apart and can now randomly float about, those are very much disordered. And so the change would be a very big change in a positive delta S. Okay, here is an example of entropy decreasing. And so if you look at this, if you have a gas and you take it and you dissolve it in a liquid, it becomes more ordered. So these are randomly about, and now they're in a smaller, more confined area, and you have less arrangements of the gas particles here in the water. Okay, so as you heat stuff, as you heat a solid and you increase the temperature, at this point, this is a melting point, you increase the temperature, this is the heat of vaporization there, and you increase the temperature. As you increase the temperature, you increase the entropy at every stage of this. Why? Because here the particles are moving faster. Here they're going from being a solid in that ordered state to a liquid where they can flow more freely. Here they're moving faster. Here they're going from the liquid state into a gaseous state. And so you can see going from a liquid to a gas has a much larger increase in entropy if you look over at this side of the graph. Okay, which brings us to this Maxwell-Boltzmann distribution again. And so whenever you add heat to a system, for example, our 1000 Kelvin temperature, you can see we have particles. If this is the kinetic energy, we have a large distribution of kinetic energies for these particles. You have some moving extremely fast, some moving a lot of them moving in the average, some moving actually kind of slow. And so you have a large increase in entropy. There's a lot more arrangements with all these different speeds, and so these particles are kind of all over. If you have a lower temperature, there's a smaller distribution, and most of them are kind of going the same speed, so there's less arrangement and motion of the particles. Okay, if you increase the volume, you increase the entropy, meaning you have more potential arrangements if you have more space for those particles to arrange. So there's a higher degree of disorder in this state with a larger volume than in the previous one where the volume is a little bit smaller. Okay, so we will get to the point where you calculate delta S. Calculating delta S is relatively straightforward. We use exactly the same equation as we did for calculating delta H. So the delta S of the reaction equals the sum of the products minus the reactants. You do have to account for the number of moles. And so let's do one of those examples. So if we look at this, if we have delta S for this reaction, you would use this equation where you have the change in entropy equals the sum of the entropies of the products minus the sum of the entropies of the reactants. Again, this equation is on your equation sheet. No need to memorize it. But it's the same as the delta H one. So what you would do is you would take your reaction and look at the products. You have one product there. And so if you look at that, you have 1 mole of the product times the delta S of that product minus. Now we're going to look at all of our reactants, and we have 2 reactants there. We have 1 mole of our nitrogen, so 1 times the entropy of the nitrogen, plus 2 times the entropy of our oxygen. And so that's what we would do. Now, where would you get these values? These values actually, you would be given a table of values in your textbook. In the appendix, you have a whole list of these values. And so if you look them up, you will find these numbers. So if we look up the value for the entropy of dinitrogen tetroxide, you would get 304 from that table. If you look up nitrogen, you would get 191.5. If you look up oxygen, you would get 205. And literally, just look it up on a list, add them all together, and you get negative 297.3 joules per Kelvin mole. The units for this would be on that table as well. And we're going to talk about those units in a minute. So now let's get to thermodynamically favored. We want to know, how can you tell? If it's exothermic, they tend to be favorable. If they make things more disordered, then they tend to be favorable. So, but neither one of these things actually tell us that it's thermodynamically favored. We need something to help us figure that out. Now there's 2 methods that we can use. One is Gibbs free energy, and that's what we're going to talk about today. But before I talk about that, I'm going to talk about the entropy of the universe. So if you have a thermodynamically favored process, the entropy of the universe increases. And so we have the system. The system is our little beaker with the stuff we're measuring. The universe is everything else around that system. So all the surroundings. If the total disorder in the universe, which is the sum of our surroundings and our system, which is typically in our little beaker in the lab, if this disorder increases, then it's thermodynamically favored. Now, if we look at this, what does that kind of mean? If you have an exothermic reaction, here's your beaker, here's our system. We know if it's exothermic, heat flows out of that beaker into the surroundings. With the heat entering the surroundings, it increases the entropy of the surroundings. So if that increases the entropy of the universe, it's thermodynamically favored. Now, if we look at an endothermic reaction, we have our little beaker. The beaker gets cold. Well, heat comes in from the surroundings into our beaker. And if it increases the entropy, then that could make it thermodynamically favored. But neither one of those things really, it's hard to measure. We can't really measure the disorder of our surroundings. That's really hard to measure. And so we are going to look at Gibbs free energy. So looking at Gibbs free energy, we can look at entropy and enthalpy and determine, is it thermodynamically favored? And so we come to this, which I call our going home to supper equation. And so if you look at that, here's going home to supper. But if we look at that, delta G is our Gibbs free energy. This tells us if our reaction will occur, if it's thermodynamically favored, if it's spontaneous. Delta H is the enthalpy. This tells us, is it endo or exothermic? The temperature of the system matters because delta G might change at different temperatures. Delta S is the entropy change of the system. Now I want you to kind of put a little star. When you get to these are pretty straightforward, kind of easy. The most common mistake people make whenever you have delta H is given in kilojoules per mole. Delta S is not. This is given in joules per mole typically, or joules per Kelvin. So you have to convert. You have to convert this one. This is the most common mistake. So make a mental note to double check, did I convert the delta S? And so let's look at these. Now, if you have delta G, if it is negative, less than 0, then it's thermodynamically favored. End of story. If it's positive, it's not. And so looking at that, this is the amount of energy that can be used to do work. This is the energy that we can make it, do something for us if we want to move a piston or, light a light bulb. This is the energy transferred as heat. Now this term is the energy used to create disorder. And so let's look at that. We're going to calculate delta G two ways. We're going to use the going home to supper. The other equation we could use is finding delta G using delta G of formation, just like you did with delta H. We'll look at both of those and talk about those. But if we go back to our going home to supper equation, you learned how to calculate delta H using calorimetry, using Hess's law, using enthalpy of formation, and even bond energies. You can calculate delta S using entropy values. And so if you plug those two in there, you can find delta G. So let's practice with that. So if we want to find delta G for a reaction, I know that the delta H of that reaction is negative 218, and I know delta S is negative 765. Is the reaction thermodynamically favored? Okay, so if you're trying to find delta G and you're given delta H and delta S, that is your clue. You are using the going home to supper equation. And so we're going to use the going home to supper equation. We know delta H. we know delta S, we know the temperature. Now the temperature is in Celsius, so we need to convert that to Kelvin. And so I'm going to go ahead and write that right now so I don't forget to do that. I'm going to convert that into Kelvin. And so if I put in my delta H minus, if I look at my temperature is 32 plus 273, which will give me 305. You can write 305 in there if you want. I just put the whole thing in there. Now the last part is delta S. Now if I come to my delta S and substitute it in, this one has the thing that I was telling you about. Delta H is in kilojoules, delta S is in joules. You gotta convert it. You can do it right here, and this would just be 0.765 joules per Kelvin, and it's a negative number. You can plug that right in, or you can do it using dimensional analysis right here in the steps, and so that's what this is. Putting all of that into your calculator, you should get a delta G of positive 15.3. And if you have a positive delta G, then no, our reaction is not thermodynamically favored. So whatever that reaction is, when you dump the reactants in together, they're not going to form products. It's just going to sit there unreacted. Okay, so now here's another example of what we could do. So this reaction is not favorable at 32 degrees Celsius, but there is a temperature at which it is thermodynamically favored. And so if you have this question, at what temperature does the reaction become thermodynamically favored? We want to know, when does delta G go from positive to negative? Now, in between positive and negative is what number? It's 0. 0 is the turning point between positive and negative. So if you set delta G equal to 0, that's the temperature at which it turns from being positive to negative. And so if we set that up, if you set up your going home to supper equation where delta G equals 0, or delta H minus T times delta S equals 0, and you rearrange that guy to solve for the temperature, you end up with delta H over delta S. And so when you have that, if you plug in the numbers from the previous problem, negative 218, you plug in the delta S, which we said was negative 0.765, and divide them, you get the temperature at which it goes from being thermodynamically favored to not. So if you had the previous reaction at 32 degrees, it wouldn't react. You have to heat it up to this temperature before it will react. Okay. Now, this little chart is kind of important. If you have something that's exothermic, and the entropy increases, it's always thermodynamically favored. So if you know the sign of delta H and you know the sign of delta S, delta H is negative and delta H is positive, delta G will always be negative. There will be no exceptions ever. Now, if delta H is positive, meaning it's endothermic, and delta S is negative, meaning there's more order to the system, it is never, ever, ever thermodynamically favored. Then we have two exceptions. Now, if you have delta H is negative, meaning it's exothermic, and it's negative, meaning there's more order for the entropy. This one is only thermodynamically favored at low temperatures. Okay, and if we go up to the equation, you can kind of reason through. You can memorize this chart, or you can reason through it mathematically. If this is a negative number, this is negative, and if delta S is negative, when these two multiply, you get a positive number. This positive number has to be smaller than this one. So at low temperatures, that makes this number smaller. So delta G is negative, and it's thermodynamically favored. If the temperature is high, this number becomes a big positive number. It's a bigger positive number than this negative number. So delta G becomes positive, and it's never thermodynamically favored. Now, when it's thermodynamically favored, it is enthalpy driven, meaning despite the fact that it becomes more ordered, the enthalpy makes it thermodynamically favored. Okay, going down to this bottom reaction, if you have an endothermic reaction, a positive delta H, and a positive entropy, meaning it's more disordered or less order. Sorry, not less ordered, less disordered, more ordered. More disorder. Then you have, it's thermodynamically favored at high temperatures. And so that means that for this one, at really high temperatures, the disorder wins. It's entropy driven. Okay, so let's look over here at some of these. So if we look at that, you can memorize this chart like I said before, or you can look to the equation to figure it out. But at a positive delta H, this is going to be a positive number. And if this is also positive, when this term is bigger than this term, you get a negative number because of this negative sign here. And so at really high temperatures, this number is bigger. And so delta G is negative. At a really low temperature, this number, this delta T, or this T times delta S term gets really small, and it's smaller. And so if the enthalpy term is bigger, the delta H is bigger, you have a positive number, so it's not thermodynamically favored. Okay, so looking at this, we have delta H and delta S given to us. We have a negative delta H and a positive delta S for this reaction. Is this process thermodynamically favored? Yes or no? How do you know? Well, you can do your going home to supper equation and calculate it, but I know that this is thermodynamically favored. If delta H is negative and delta S is positive, there are no exceptions to where it's not thermodynamically favored. Every time I calculate delta H, doesn't even matter what the temperature is, I'm always going to get a negative number. So if I want delta G is always a negative number. Okay, let's look at the other way for calculating delta G. The other way is similar to what we've done before. If you want the delta G of a reaction, If you take the sum of the delta G of the products minus the sum of the delta G's of the reactants, taking into account the ratio of moles, then you can figure out delta G. Now here is something. Delta G for an element in its standard state is 0. So it's 0 in its standard state. So looking at this, here we go. Here's the thermite reaction. We did this one in class. So we have iron oxide and aluminum solid. When they react, you have the aluminum oxide formed and some iron solid formed. And so if you want to know if it's thermodynamically favored, then you would look up those values and plug them in. So if we look at that, to write the delta G, you would need to write the delta G of reaction is the sum of the products. Now if we look at our products, we have two products. We have 2 times the delta G of the iron plus 1 times the delta G of the aluminum oxide. So those are our two products, minus the sum of all of our reactants. So if we look at our reactants, we have 2 of them. We have 2 times the delta G of the aluminum, and then we have 1 times the delta G of the iron oxide. Now, if you look up the delta G values, you will either be given a table. These come from your book. If you look them up in the appendix of your book, there's a whole list of compounds and their delta Gs. And if we do that, you will see that these values are in there. Now, okay. Okay, so if you have a solid, we have a delta G of 0 for that one. So right here we have a delta G of 0 for the iron. If you look up the value for the aluminum oxide, it is negative 1,582. If you look up the value for aluminum, since it's a solid, it's 0. It's the pure element. And so these two we could have written as 0 from the beginning. This one has a value of negative 743. Again, that comes from the table. And so the delta G of that reaction is negative 838. Now this is a spontaneous reaction, and if you remember, you did have to give it a little bit of activation energy, but after that, a lot of that reacts. So you get a tremendous amount of energy. Okay, now just because it's thermodynamically favored doesn't mean it's fast. Some things are under something called kinetic control, like oxidizing. Rust is a thermodynamically favored process. It can take hundreds, thousands of years for something to rust away into nothing. So it doesn't mean it's fast. Sometimes delta G is positive and the reaction will occur if we add energy. For example, if you add in electricity to recharge a battery, recharging a battery is a delta G that's positive. Removing an electron from an atom is a process that has a positive delta G, but if you add in energy in the form of photons, then you can make that reaction happen. And if you look at the conversion of carbon dioxide to water and water to glucose, this is not a thermodynamically favored process. But what happens is this overall reaction occurs in a lot of steps, and the sum of all those steps creates an overall thermodynamically favored process where you absorb some energy in the form of energy from the sun. So here's a little summary of the stuff we were talking about earlier. And so You can look at that. I want to move on to this one. Um, if you have enthalpy, that talks about the energy of your system. If it's positive, it's endothermic. If it's negative, it's exothermic. We talked about entropy today. That is the disorder of a system. If it's positive, there's more disorder. If it's negative, there's less disorder. Delta G means the amount of energy available from a reaction, the amount of energy to do work. And so that tells us if it's thermodynamically favored or not. If it's positive, it's not thermodynamically favored. It's not going to happen. If it's negative, it's thermodynamically favored. It will happen at those conditions. If we look at equilibrium, equilibrium tells us the extent of the reaction, how much the reactants become products. Do a little bit, do all of them? I don't know, it depends. If you have a number less than 1, it favors the products. This is associated with the thermodynamically favored process. If it's less than 1, it favors reactants, meaning you don't have a whole lot of products being formed. So that is the end of Thermodynamics 3. I will see you next time.